All right, I think we're ready to begin here. I'd like to wish everyone a good morning, a good afternoon, a good evening from wherever you're joining us from today. Thank you for joining. My name is Christopher Ulrich, Space Products Account Executive for the FreeFlyer team, and I'd like to welcome all of you to our Optical Comms webinar here today. In this webinar, we're going to be utilizing FreeFlyer 7.10's optical communications modeling capabilities to consider how off-the-shelf optical components might be used to complete a link between a lander and the moon's surface and a station on Earth. Optical communications enable low power, they're secure, and high data rate connections between spacecraft and ground stations. But despite these advantages, optical communications can be more technically challenging than radio frequencies, which are typically used in spaceflight. Atmospheric scattering, turbulence can relate to signal loss, and there are also significant trade-offs between smaller beam divergence and also pointing errors. Now, optical receiver modeling and modulation choices are also crucial for determining the ability to close the link. And today we're going to get a great introduction to optical comms by our speaker, Nathan Griffith. So a little bit about Nathan. So Nathan is a senior space products software engineer who's working on the FreeFlyer team here at AI Solutions. Nathan studied cosmic ray physics at Ohio State, where he received his PhD back in 2015. In 2016, he joined Leo Labs, becoming their primary orbit determination engineer. And after joining AI Solutions in 2024, he's been the lead developer for optical communications modeling in FreeFlyer. So I'd like to welcome Nathan to the conversation today. And Nathan, I will pass it to you to take over and take us through optical comms.
All right, fantastic. Yeah, thanks for the intro, Chris. I will jump right into it and kind of talk about some of the context that Chris introduced. So yeah, why would you select optical communications? The main thing, right, is that your wavelength of choice has become quite a bit smaller, and that means that basically all of your components are going to have their swap considerations reduced. So your size, weight, and power are all going to go down in an optical communications package, and you're still going to be able to achieve high data rates with that. Another thing that's an advantage of optical communications is that instead of with a high gain radio antenna, might still bathe half a continent in the information that you're beaming down to the surface of the Earth. But with a laser communication system, you have much higher gains, which means much smaller footprints on the ground. So, potentially you could be looking at, hundreds of meters on the ground where your signal actually is located. So just in terms of physical security, it has that capability as well. All right, so yeah, and again, to kind of reiterate what Chris said, we're going to be considering a toy scenario today, which is basically we would like to consider this problem of if we have a small video-capable rover on the moon, can we, via a lander, beam real-time streaming video in HD quality back from the surface of the moon direct to the surface of the Earth? So that's what we'll be considering. Although first we're going to back up and just kind of talk through some of the fundamentals of optical communication. So the general problem statement, right, is, it's similar to RF. How much data can we transmit over this channel? How far can we transmit it? So can we get it from the surface of the moon to the surface of the Earth? And then what potentially gets in the way of us wanting that data to go as far and, as fast as we want it to in terms of bit rate? So, spoiler, the atmosphere tends to get in the way for optical communications in a way that it makes it unique compared to RF. So we'll be talking about that. So a useful tool when you're discussing an optical link and any kind of communications link is this mathematical construct called the link margin, which basically runs all the way from your transmitter power all the way through all the gains you might get from the transmitter itself and the receiving end, and then any losses you accrue in the middle. And then you subtract away the sensitivity of your receiver. And that basically tells you if you have a positive number and your link margin is positive, then that means that you're above your performance threshold and you can absorb some, extra losses that are unanticipated and still maintain your performance of your signal. However, if you do this calculation and you end up with a negative, then that means you've got a little bit to make up. So you've got to find some place in your chain here to make up that difference in order to hit the performance threshold that you have in mind. So first we'll talk about gains, which were the positive terms in that equation. So we have to talk about kind of the start point and the end point of a laser communication system. And so the transmitters are lasers, obviously. This is a photo of one of my own laser pointers and me trying to blow up the moon with it. So these are intuitive everyday objects. We all know, we've all held a laser pointer. We know that they have a really small beam width and they're really bright. And that it's that exact capability that is going to lead to a high gain from a laser transmitter. In terms of the receiving end, the bulk of that component is going to be a telescope, basically. So again, here's one of my telescopes. So that is going to be kind of the thing that takes in your light, and you're going to get your gain basically from the diameter of that telescope on the receiving end. So there's other stuff that goes into it, but those are kind of the bulk components that make up the beginning and end points of a laser transmission and where the gain comes from in this connection. In terms of losses, we are always going to have free space loss, just like we do for radio communications. And it's just a fact of math and physics that you're creating a signal, and that signal essentially gets projected along the surface of a sphere, and you get losses just based on that happening. So you're always going to have this to deal with, no matter your environment. But again, like I said, with laser communication, atmosphere is important. And so we need to talk through a few different aspects of what happens to this optical signal as it passes through the Earth's atmosphere. So the first of these we'll talk about is actually one that we don't model in FreeFlyer, but it's important. And I want to talk about why we don't model it. There's a place you could inject losses like this in the code. But yeah, basically, as this laser light hits the atmosphere, it's gonna encounter molecular gases in the atmosphere, and those molecules tend to absorb certain wavelengths of light. So on the right here, you can see a plot where you have all the light that comes in right at the top of the atmosphere, and then you have what you actually get at sea level, and you can see all these little dips and carve outs that correspond to different molecular gases in the atmosphere. So if you happen to choose exactly the wrong wavelength, you're going to hit one of these carve outs, and your signal is going to get absorbed by the atmosphere, basically. The good news is there are places in the optical continuum where this loss is negligible. And so if you were to buy, kind of standard optical equipment off the shelf type stuff, you're almost certainly going to get something that falls within this window automatically. And so it ends up being an effect that you don't have to worry about so long as your equipment has selected one of these frequencies, or you've designed your equipment to select one of these frequencies. Here I've called out on this plot a wavelength of 1550 nanometers. That is in the infrared range, and that is a super popular frequency for both terrestrial links, so surface to surface, free space optical, and for space-based, operations as well. So actually, everything we talk about in the rest of this webinar is we're going to be assuming it's 1550 nanometers. So the good news is, yes, tricky part of laser light propagation through the atmosphere, but we don't have to worry about it as long as we select our frequency correctly. Okay, so there is another unavoidable part of atmospheric loss, and that's just basically the loss you're going to get from scattering as that light moves through the atmosphere. The good news is there's a very commonly used expression that parameterizes this atmospheric loss in terms of a really common meteorological parameter called the visibility, which is exactly what it sounds like. It's basically how far can you see, and there's obviously a rigorous definition, but it's basically how far can you see at ground level, and or I guess it'd be up to, but this is super commonly available. It's like every small little airport or big airport, you drive by, they're going to be deeply interested in this because it matters a lot for air travel. So it's a standard, easy to attain parameter, and it plugs into a relatively simple equation, and that'll allow you to get your atmospheric loss. There's another even more subtle effect of the atmosphere, and this one is called scintillation. And as an amateur astronomy, this is one of my personal enemies. Basically, it comes from the fact that as light propagates through the atmosphere, it's going to hit little bubbles of kind of turbulence in the air, and that turbulence is going to cause the light signal to wobble and smear out. So, in my personal experience, this makes a difference between a really nice picture of Jupiter and a kind of crappy picture of Jupiter. So those are two of mine on two different nights with two different conditions. In terms of like, if you were to look like at monochromatic light and how that would look, instead of a bunch of different frequencies like the above, then you can see that, without turbulence, without scintillation, you would have this, beautiful beam here, and then on the right, you see it gets all scattered out and smeared. So as well as getting scattered out and smeared, it also causes time series fluctuations. Like I said, it kind of wobbles, and so your signal is going to dip up and down. The good news is this can be modeled. I will spare you the integral that you have to do it. But basically, in FreeFlyer, we have two different ways of handling this atmospheric scintillation effect. So one is you come in and you say, I don't want scintillation to affect my signal at 99.999% confidence. And then we have a function that will come back and say, okay, given your system, you need this much more link margin if you want to be 99.999% sure that scintillation is not going to cut your signal at any given time. And the other way to do this is the complete opposite, right? Like, let's say you have your link already set up and you're like, all right, this is the margin I've got, right? Based on that expression we saw on the other slide. This is the margin I've got. Now, how often is scintillation going to come in and give me a hard time? Basically, what's the percentage of downtime that I can expect from scintillation given that situation? Okay, so another thing that Chris alluded to, modulation is a important parameter in an optical link. In optical communications, especially deep space optical communications, modulation of the signal, it tends to not be too fancy. In fact, a lot of them are essentially just blinking the laser, and so that's amplitude modulation. There are a number of different ways to blink a laser, as it turns out. But a few of the commonly used ones are something that's just called on-off keying. So these are the top two here. And that's basically you turn the laser on if you're sending a 1, you turn it off if you're sending a 0, and you can keep the 1 signal on for the full symbol duration window, or you can keep it for half, and those have slightly different characteristics. Another very popular one is something called pulse position modulation, which means you basically take your window and you divide it up into little sub windows, and then you flash the laser corresponding to the number that you want to send in that window. Here I'm sending 0, 1, 2, 3, a 3, and then here I'm sending 0, 1, 2, a 2 in that subsequent window. So one thing that's nice about pulse position modulation is that since you're only flashing that light, every once in a while, you end up with a much lower average power consumption. So this ppm thing tends to be pretty attractive if you're doing deep space stuff, just because power is always something that's on your mind if you're running a spacecraft. So amplitude modulation isn't the only story, although we don't get too complicated with kind of the wave properties of light. Like I said, in general, things are kept pretty simple in terms of modulation in optical comms. But one you will see occasionally is something called differential phase shift keying, which is basically this instead of messing with the amplitude, we're gonna change the phase of our signal. And so what we'll basically do is say one phase corresponds to a 1, and then a phase that's off by pi or 180 degrees, that's going to be a 0. And basically, you can just wobble it back and forth, and whenever it flips 180 degrees, then you're sending a different data point, a 1 or a 0. So this is just a simple example of that. In terms of types of receivers, there's a number of these. Kind of roughly speaking, there's kind of two large families of optical receivers. One is direct detection, which is like the intensity of the light is what you're detecting. And so you look at those, like that first slide I had of modulation, amplitude stuff, those are going to be, direct detection friendly modulation formats. There's also coherent detectors, and those are this is kind of thing, homodyne, heterodyne. These are, if you're into radio, you've probably heard this kind of stuff, but basically you can mix the incoming signal with a local oscillator, and those receivers have different properties, and you can extract some of the wave nature of light doing that kind of stuff. So in this talk, we are going to constrain ourselves to a kind of direct detection receiver called that uses a component called an avalanche photodiode. And basically, an avalanche photodiode takes in photons and via some semiconductor magic takes those photons and turns them into a lot of secondary electrons. So you can use you can basically get a multiple on your versus how many electrons you get versus how many photons you got. So we'll be focusing on those because they're pretty common. And I'm not going to dive into this equation, but just to say, here is how you would model the signal to noise ratio in a avalanche photodiode receiver. So basically, just to kind of point out the parts of this thing, you've got your signal up here, up top, and then you've got a couple different sources of noise on the bottom. One of these is shot noise, which is sort of related to the input signal. And then another one is thermal noise, which is the noise that you get for free just by assembling an electronic circuit. So both of those end up mattering in an APD receiver. And this is sort of the underlying, one of the underlying physical models for the stuff I'm going to be talking about in subsequent slides. Okay, so let's circle back now that we've kind of talked through all of the ingredients that go into optical communications. We'll circle back to our toy scenario now. So again, the idea here is we're gonna put a rover with a video camera on the moon, and then we're gonna have a lander that landed the thing. And let's say between those two, the lander and the rover, we have just a traditional RF, signal. No reason to use anything too subtle. But then from the lander to the Earth, we want to try an optical connection. So what we'd like to know is, if we're pretending we're, one of these kind of new says lunar startups doing landers and such, usually you don't want to reinvent the wheel if you're selecting components for your spacecraft. So a question that I asked myself here, just to make it fun, was, could I pick stuff that's kind of readily available that has product pages, spec sheets, stuff like that, stuff you can order online, essentially. And then the other question is how much power are we going to need to do this? I've heard that, optical communications uses, less power. Does the math bear that out? And just to mention the photo here, there's no affiliation with Firefly Aerospace. They just have this adorable photo that has all the parts that I was talking about here. So it's a neat photo, and I included it. Or rendering, I should say, not photo. Yeah. So what we're going to do next? Oh yeah, that's right. So we got to go shopping, right? I said we're choosing off-the-shelf components. So this is me just kind of searching around the internet and looking for stuff and finding their spec sheets so I could use them in the software simulation. And where available, I've called out some prices here. So there's an outfit called Thor Labs. They sell a bunch of optical equipment. They sell optical receivers as part of their catalog, and they have an avalanche photodiode receiver that'll run you about $2,000. Like I said, for the receiver, that's a telescope basically, so you don't have to overthink this. I went with a very nice Celestron Schmidt-Cassegrain. This is the kind of thing any amateur, if they had enough money, they would probably buy this thing. It's not hard to get at all. Um, yeah, in terms of the transmitter, it was harder to get a price on that one, but I kind of put on my old astrophysics hat and said it's about the order of $10,000 probably to get a optical amplifier that'll do bursts of 20 watts. And then finally, you need a fiber collimator, which is basically the thing that focuses the laser, and then the quantity, the figure of merit for the fiber collimator is basically how small is the beam, and it's about 25 microradians on that thing. So I couldn't find a price for that, but they had a nice website, and I'm sure if I asked for a quote, they would oblige me. All right, so so we'll take 1 minute, and I'm not gonna dive super deep into bogging down in code, but I wanted to show you real quick how all this would work in FreeFlyer. So here I've just kind of copied and pasted bits of code that are in the simulation that I'm about to show you, just to show you what the interface looks like in general terms. And it's, it is, if you've used FreeFlyer before, a lot of this, patterns are going to look very similar. So this is a super object-oriented setup here. So we're declaring an optical link object. We're saying what our wavelength is. And then we have a bunch of figures of merit for our receiver. And we have a bunch of figures of merit for our transmitter. And, like I said, I basically just pulled those off of spec sheets and put them in there. And then over here, we can do various stuff like set our modulation and various, parameters with the modulation. And, do stuff like compute the sensitivity of our receiver, for instance. So anyway, that's what it looks like. This is just a very small portion of the demo script that I made, but just to give you a sense of what it looks like. All right, and so now we're going to move on to a pre-recorded video I have of this simulation script actually executing. And I'm going to talk through all the various windows here. But basically starting out on the left, we have just kind of a console printout of various kind of interesting stuff that was either an input or was a calculated quantity along the way to just kind of like help you diagnose if you're picking out components, what's going on here. So one thing I didn't talk about that is an important input parameter to a optical comms simulation is something called the bit error rate, which basically is how often you are going to flub a bit in your connection. And this is just it's a statistical certainty that you will mess up a bit every once in a while. And if you're, if you've really ever had to dive into Wi-Fi troubleshooting problems, you may have come across this figure. So anyway, for this link, I've chosen a bit error rate that is like good terrestrial Wi-Fi, basically. So 1E minus 9. So that was an input to this simulation. What we're going to do here is just kind of talk through the rest of the plots. In the middle here, that was just a nice animation showing that whenever the moon and the Earth, the station on the Earth and the station on the moon are in line of sight, we get this nice little line drawn between them just to kind of visually indicate how that looks. And we see how the Earth spinning around in front of the moon looks. So it's just a fun visualization. On the right here, here's all the fun plots. All right, so another thing I didn't talk about in terms of a challenge for optical communications, but is evident in this plot and explored pretty thoroughly, is the fact that you basically end up with a trade-off because your laser, right, on your, let's say the laser on our lander, right, is ultimately going to be mounted to a mechanical piece. And that mechanical piece is going to have some tolerance, which means it's going to have some built-in errors in how precisely it can possibly point, right? So we also said, right, that more, basically in one of the earlier slides, we saw that equation, and basically more gain is good, right? Because it gives us more margin. And the way you get more gain with a laser is you make the beam narrower and narrower. So you have a problem here because the narrower you make your beam, the harder it is to point. So eventually the gain that you get from making the beam narrower is going to fight the mechanical error in having to point the thing. So you end up with a non-monotonic function with a maximum. And basically what I've done here is take those two things together, both the gain you get from the laser um, on the um, on the x-axis here, and then the loss you get from assuming a certain um, pointing error in the mechanism that actually points it. So these are all built-in things that you can model in FreeFlyer. And what I've here done here is just sum them and call out the exact component that I selected for the laser collimator. And so the idea here was to be like, all right, theoretically there's a perfect component that could be selected to match to a realistic mechanical pointing error, and how far did I get away from picking that perfect component as I was, selecting my parts with spec sheets. And so the good news is here that we're not terribly far off from what the actual like perfect component selection point would be here. So that will say that's an important part of laser communications is this pointing thing, and it's something that you can investigate pretty trivially in FreeFlyer. I'm going to skip the middle plot because that's kind of the fun one to end on. And then at the bottom here, this is just some mocked up meteorological visibility, which means it's like procedurally generated by me just making a function that has diurnal variation and shows, day over day a change in the average visibility. So because that feeds into the kind of the middle plot I'm going to talk about here, which is an estimation of the maximum bit rate you could get from various modulations that you could select. So we talked about PPM here, and these kind of dominate the spot. And I didn't talk about it in detail, but we showed a 4 ppm example in the modulation slide. So that was 4 subdivisions, but you can go up into many more different subdivisions. And here we've gone all the way up to 64 ppm, so you'd have 64 subdivisions. And so it's probably going to get harder to design in terms of like you're going to have basically a tighter timing tolerance. So that's an interesting parameter you want to look at. So it looks like here, if we go to 64 ppm, we don't have to go higher than that if we want to begin to close this link and hit what I've called out here in this kind of tan orange line as the HD video rate of 5 megabits per second. So it looks like we could actually get, based on these components that I've selected, we can hit our target of 5 megabits per second if we go with a 64 ppm modulation. But one thing that's going on here is our visibility is decreasing over time, and you can see that these correlate, and less visibility on the ground means a poorer max bit rate available to us. So now I wrote a sequel to this too, because of all the stuff we talked about, all the different effects that we incorporated in the last simulation. What we didn't take into effect was that tricky scintillation thing I talked about earlier. So this time I'm going to do a very similar analysis, but I'm going to lock a couple things down. I'm going to lock us down to 5 megabits per second, which is our target for HD video. And I'm also going to say we want a 99.9% scintillation uptime. So these two figures are going to go into that. And I'm also going to go with 64 ppm, which was the winner from the last slide. So we'll also lock down that modulation. And what we're going to see here is a very similar analysis. Again, here's the pretty animation showing when the link closes. And then we get a number of plots here. One of these is how much scintillation margin I'll want to add for a 1e minus 3 outage probability, which corresponds to 99.9% uptime. And then if we add that additional loss, right, from the scintillation margin that we need to add, and we take that away from the link margin, and then we just color code it for like, all right, when is our link margin above 0, accounting for the fact that we need this extra buffer for the scintillation loss. And I just color code it as green whenever it closes. And so even taking into the scintillation loss and looking for 99.9% uptime, we can still see that we can close our link, although not all the time. And you can see here, just like the meteorological effects from the visibility were not helping us. Here we see that the elevation of the Earth or sorry, this is actually the elevation of well, now I got to think. I think this is the elevation of the yeah, it ought to be because it's correlated to the scintillation loss. The elevation of the station on the moon from the position of the Earth, and so we can see it gets lower and lower in the sky. And as it gets lower in the sky, we've got more air to push through, right? So our scintillation is going to bother us more and more. So this is another thing that correlates with a, something that makes your signal harder. So the takeaway seems to be you can do this with off-the-shelf hardware, but you're going to want to pick a favorable ground site, um, and you're going to want to pick a time during the month when the moon is pretty high up in the sky. And yeah, just so you have less scintillation to deal with. Okay, yeah, so we talked through a number of different things, at which I won't go through here in detail, but we have shown that if we stick to off-the-shelf components for our little toy scenario of beaming HD video back from the surface of the moon to the surface of the Earth directly, that is something that's technically achievable. So yeah, this has been a really fun topic to learn about over the past year, and it's been a really fun demo to put together, especially with all the excitement around says lunar stuff. And yeah, I'd love for somebody to give this a shot. I want to see that live video from a rover crawling around the moon. And yeah, one last thing, I just want to shout out this paper, which had a similar premise, and I used it as a jumping off point. Basically, instead of going direct from the moon to the surface of the Earth, they went from the moon to a geo orbit. So I just basically took their premise and ran with it the extra few miles down to the surface and to investigate the other effects. So anyway, cool paper, good thing to read if you're interested in this kind of stuff. And at that point, we will segue to any Q&A, any questions people come up with.
Yeah, thanks, Nathan. Thank you for the presentation, Nathan. We got a couple questions. First one being from Ari. How is solar blinding of optical links modeled in FreeFlyer?
Yeah, that's a great question. We do include a capability for actually not just solar blinding, but blinding from any bright source. So like for instance, if you wanted to do Venus, or if you wanted to do like just like background sky radiation, there are hooks in the script to do those things. So yeah, there is a there's sort of you remember this in our model from a few slides back. There's sort of an elaborated extension of that model, which can incorporate the addition of sunlight. If you happen to like get real unlucky and you're pointing your field of view of your receiver directly at the sun, we can model that. It obviously it's an interesting thing because it really comes down to what kind of receiver you've chosen. So there are separate physical models for like say APD receivers versus preamplified or heterohomodyne receivers. Those react differently to sun in field of view, but it is something we can model. And one thing that I just on a personal note, one thing I found really surprising doing the research for this is that for certain types of receivers, preamplified and heterohomodyne, you can actually it is not as big an effect as you would think to have the sun directly in the field of view. So pretty cool stuff.
Cool. And we have another question from Vest. What are the current FreeFlyer capabilities to handle in a simulation sun outage event in which sun is behind the transmitter or the receiver during an optical comm session and the related link disturbance, especially for inter-satellite optical links modeling use cases?
Yeah, that's great. Another sun question. So in terms of basically what I'll just kind of elaborate on the first bit. So one of the things it does is that basically as the sun comes in the field of view, your sensitivity goes down, and so that's like one of the things I've worked on to kind of just make sure that everything's working as it should is to model the sensitivity versus time as the sun drifts through the field of view of the receiver, and then you can see The sensitivity, I'm just making up numbers now, but you could, for instance, see like if you had a minus 60 dBm sensitivity in a receiver, and then if the sun's in the field of view, all of a sudden that's going to be like, maybe a minus 40 uh, dBm sensitivity receiver. So you're going to see that, you're just not going to be as sensitive when the sun's in the field of view. Yeah.
Thanks. Another question. Earlier you mentioned you said the script was a small portion of the total script. How much scripting is required and how hard is it? And are there examples, or do I have to start scripting from scratch?
Yeah, so as is typical with a FreeFlyer release and new features included with 7.10, there will be something we call a sample mission plan, which is basically a prefab, pretty robust utilization of the feature. So you'll be able to use that as kind of a attraction point and to see how how it functions. If you want to get a sense right now of how optical communications works. It is similar, although not identical, in design to an existing feature in FreeFlyer, which is the RF link object. So that, and a lot of the bones are kind of similar, where there's a transmitter, there's a receiver, you've got to set a reference object on either end of those to be like, hey, where's my transmitter located? Where's the receiver located? And if you've worked with FreeFlyer before, you'll know the scripting language. But if you don't, it's its own proprietary language, but it is not. It does not have a high learning curve. It is something similar to, say, like Python or so, if you're familiar with that kind of stuff, or MATLAB. Yeah.
Thanks. Another question from Dave. Is it possible to vary local atmospheric turbulence parameters, e.g. like R0, for each ground station?
Yeah, that is for each ground station I would have to think about. Yeah, actually you should, because you would set up, sorry, this is a little bit inside baseball, but you would set up a different optical link object, I believe, for every ground station connection. And every optical link object has basically a built-in object that represents all the atmospheric parameters. And one of the input atmospheric parameters is the ground turbulence. So that has a sensible default value, but that's something that you can actually input your surface turbulence, and the equation is, if you do optical comms, you're probably aware of this one. But again, this is deep inside baseball if you don't. But yeah, it uses the Huff-Nagel Valley equation, and you can set the C0 of that equation using the atmospheric object. Yeah, that's associated with the optical link object.
Another question from Corey. So optical link object can report AOS or LOS events like RF link?
LOS events. Someone else might have to speak to that if they know who's on the call. I'm not sure that's a built-in on RF link. That might be a different FreeFlyer capability.
So Nathan,
No.
to jump
Yeah.
in here, I do know that the ground station
Yeah.
object in FreeFlyer, right? So for instance, a ground station is used to identify that contact duration, the antenna
Yeah.
pointing, the AOS, LOS information. But yeah, we can definitely incorporate that with our sensors when trying to communicate with a ground station.
Yeah, I thought that would fit in pretty easily. Just wanted to be sure. Cool. Yeah, thanks.
And from Raj, does it support real-time integration with external tools or sensor models for these scenarios?
Yeah, so in terms of external tools, sensor models, those are, well, yeah, I think actually I'd have to look at the software, but in general, it has been a design philosophy as I made this stuff to kind of have different hooks where you can kind of fill in your own values if you prefer it. So I'd have to look. It would depend probably on what you're trying to do with a custom sensor model, and I'd have to look at the code to give you a good answer off the top. But unfortunately, I don't have that just in my working memory right now. But in terms of like external models in general, like for instance, if you wanted to do a sophisticated time varying weather model on the ground, there is basically the visibility that I talked about for the atmospheric scattering. That is just a variable that you can set, and so you could have, FreeFlyer is very robust in terms of being able to access external data sources. It has an API and all this stuff, so you could hook in to an external, like weather simulation probably and pipe that in. So you can just choose a sensible, default value if you're just playing around, or you can, put in whatever you want and potentially get a very sophisticated output.
Thank you all for attending today. We greatly appreciate your participation and collaboration. As a reminder, we will provide the recording and slides within 24 hours to all attendees and post to our YouTube page, so please subscribe. If you have any questions and wish to contact us, you can email us at sales@ai-solutions.com, visit our website, freeflyer.com, or call us on the number on the screen. Again, thank you for joining our FreeFlyer Quarter 2 webinar today. This concludes our webinar for today. Have a great day.